Hello. Can you see me? Right there? Hello? Is it working? Hey, there's it going. Okay. Hi, welcome to this video. This is the last video, 2-4, which is the limit definition of the derivative. Today in this video, we're specifically going to look at the alternate form of the limit definition. And this is helpful if we're looking at one specific point for a function. So let's go ahead, let's look at an example right now. And here's just a reminder of the alternate form of the limit definition. And here we have delta x, and it's essentially the same thing that we looked at before, where I have a value of c, and I want to take the difference between x. Okay, and then your delta y value is the difference between the function outputs f of x and your f of c value. So we'll go ahead, we'll look at this, and again, this is useful if you want to calculate the derivative at one specific point. If we're calculating the derivative with respect to t or to x and not one point, we need to use the other form. But here we can use the alternate form. So let's go ahead and look at this example. So this says if f of x is equal to x cubed, use the alternate form of the derivative to find f prime of 3. Okay, well, I know that the limit as x approaches 3 is equal to, and I'm going to use this form here. So here's the alternate form. So f of x minus f of c, and in this case, our f of c is 3 over x minus c, which is 3. So now I'm just going to go ahead and I'm going to do some substitution. Okay, so this is equal to the limit at x approaches 3 of f of x. Okay, so our function, let me do some highlighting here. Our function f of x is x cubed, so we'll substitute. Okay, there's some substitution going on. And then f of 3, well, 3 cubed is 27. You like the Spanish? All right, there we go. Okay, over x minus 3. So what we have to do here, we have to do some reduction, some reducing, and unless you know your difference of cubes, what we're going to do here is some long division. So I'm going to go over here. We'll do a blast from the past. X minus 3 dividing into x cubed. I don't have any x squared terms. I don't have any x terms, but I do have x to the 0 terms. That's 27. Okay, so we're going to go ahead and do some long division. X goes into x cubed, x squared times. Okay, so I'll distribute, giving us x cubed minus 3x squared. We'll change our sign. This becomes negative. This becomes positive, and I get positive 3x squared. Going to bring down the 0, okay, plus 0, and then x goes into 3x squared 3x times. Okay, hey, can you see me? Okay, 3x, and then I'll multiply, so 3x squared, 3x times negative 3, that's negative 9x. We'll change our signs, negative, positive. So I have 9x, bring down the negative 27, and then I have to divide 9x by x. That gives us plus 9. 9x, 9 times negative 3, negative 27. Look at that. What? They cancel. A remainder of 0, that means they are factors, okay? And we know this. We knew it was going to happen. So we get, hey, Gil. Okay, so we get limit as x approaches, I'm going to zoom out here, okay, as x approaches 3, so I'm just rewriting this numerator. The numerator is now x minus 3 times that quotient x squared plus 3x plus 9, okay, that helps you factor it, divided by x minus 3, and then we get some cancellation going on. All right, giving us the limit as x approaches 3 of x squared plus 3x plus 9. Okay, and since this is a polynomial, it's continuous everywhere, I can just go ahead and evaluate my function. I can plug it in, plug it in, plug it in. 3 squared, that is 9, plus 3 times 3, 9, plus 9. I'm glad those are 9s and not 6s, that'd be weird. Okay, or not weird, just creepy. Maybe not creepy, just numbers. Creepy. 27 is your answer. Okay, there's the alternate form of the derivative, the limit definition. Again, useful if you're finding it at one location. If you're using it for a variable for multiplications, can't use it. Got to use the previous video. All right, catch you next time. Peace.